let's not forget the context. What is the question that we are asking? Okay, let's go back. Does showing the top 10 impact time spent on Netflix? We haven't answered that yet. All we have done is we are following the randomized control trial approach, wherein we learned how to split all the users who are coming in a streaming fashion into control and treatment. And we agreed that this split will be uneven. That's where we are right now. Okay, so let's continue. Now let's collect data. This is where things get interesting. So I have my control, right? I have my control, I have my treatment. So let's assume there are n users in the control. I'll just represent control with n here. In my treatment, okay, I have, let's say, m users. Oftentimes m and n can be different. In some cases they can be same, but oftentimes m is significantly smaller than n in most real world applications in the internet space. So now I have n customers, right? I have n customers in the control. I have t customers or t users in the treatment. Now for each of them, okay, again, control, there is no top 10. The treatment has top 10. Let's not forget that, the top 10 panel. Now for all the customers that are there in the control, I'll calculate or I'll observe. I'll see how much time they're spending. The first user in the control, how much time has they spent? Second user, how much time? Third user, fourth user, so on and so forth. Okay, these are observations. This is data that is observed or collected. Similarly, for the M users in the treatment, we collect the actual time spent on the website in that session, which means when they signed in, when they saw top 10, how much time has the user spent? Some people binge watch, some people spend less time, and so on and so forth. Okay, we collected. This is the data collection part. Again, in the medical space, the problem is similar. Okay, in the medical space also we collect data, right? So for example, we want to give vaccines to 2 to 18-year-old kids. We have 1,000 kids in the control, 1,000 kids in the treatment. For 90 days, we observe these kids. We collect tons of data. Were they infected by COVID? Did they have high fevers? How is their metabolism? Did anybody have side effects, whether it's sickness, whether it is weakness, whatever it is? We collect all of this data, right? Also, what is the objective of vaccines, especially for COVID? The objective is that while some people might get COVID, the severity of the COVID infection itself is not very severe. So we'll count things like how many people died, how many people got hospitalized. Tons of metrics are actually observed in this setup. Okay. So in the case of Netflix, which is much more easy to understand, we collect all this data. That's the second step. So first step, we break customers into two groups, control and treatment, collect data. Now, okay, here is a very interesting part. These are all observations, right? These are n observations. Now let's define a random variable, xc, x superscript c. This is a random variable which is taking these values. These are observed values of this random variable. I'm just giving a name to it. Okay, just like the way we use variables, right, in programming. This is the name of a random variable, and these are the values that we observed for this random variable. Okay. Again, whenever I say xc, I mean all of these observations, just as a simple notation. That's it. Okay, just connecting you to your 11th and 12th class. This is a random variable. These are observations. Cool. Now, what do we want actually? Look at this. Again, what do we have? We have time spent for customers or users who are in the treatment. We have time spent by users in the control. What do we actually want to measure if you think about it? We want to answer this question. Is XT, or are the time spent by users in the treatment where we have the top 10 banner, are these times greater than XC? This is what we want. But the question here is, what does greater mean? These are not numbers, for God's sake, right? If somebody tells me 20 and 30, I can say 30 is greater than 20. That's easy. But what we have is not single numbers. What we have are n observations for this random variable. What we have here is m observations for this random variable. So what does greater actually mean? That is a very important statistics question that we have to think of. There are many ways of defining the greater here, right? There are many ways. There are many ways of defining. We'll see a lot of ways of defining today. Okay, one way is, can I say that the mean or the average time spent by all the users in the treatment is greater than the mean of all the users' time spent in control. So if you think of xc as a random variable, this is the average or the mean of the random variable. If the mean of xt, you remember, whenever I say xt, I mean all the users in the treatment. Whenever I say xc, all the users and their time spent in the control group. Okay. Again, I'll not repeat the same statement. I'm just trying to simplify it for you. Now, one way, there are many ways of measuring it. There are some which are rigorous, some not so rigorous. So is the mean of xt greater than mean of xc? Again, what are we comparing here? We are comparing only the average value here. We are not comparing all the values. We are just comparing the average value. Now, some of you might say, hey, mean is a terrible metric to compare. Why is mean a terrible metric to compare? Like, very logical. That's a good point. Typically, time spent. So if I say time, again, my time variable is x, right? X is the time spent. So time spent on this website, typically, not always. Again, we don't know the actual data because Netflix doesn't disclose that. But a gut feel here is a lot of people will spend maybe a few minutes, but there will be a few people who will be binge watchers. Okay, what I'm drawing here is a probability density function of the time spent. This is nothing but time spent on Netflix in one session. Lot of people might typically spend lot of people. This is basically a probability density function. Okay, the higher the value means, suppose if this value is 20, which means many people are spending 20 minutes, while very few people are spending, let's say, 200 minutes. Okay, so that's what it means. So what happens is there will be a few people here who are binge watchers. There is some crazy Netflix series who are going to spend crazy amount of time. But most people may not spend a lot of time. Some people might just see, hey, what is there, and then sign off. Like people like me, I hardly spend any time on these because unfortunately I don't have time and I'm not super interested also. Right? So I might spend just 1 minute just to see, hey, what is in there? Somebody saying this is good, that is good. I might spend 1 minute and get out. Some people might spend 200 minutes or even 2000 minutes. So this data typically will have this sort of skewed distribution. Again, this is not from actual data. This is just from the intuition of how the problem might work. This is from our own intuition, right? Now, here what happens, there are some observations that are extremely large. Okay, there might be one user who might be spending some 2000 minutes, I mean, crazy large time, binge watching some new series. There are people who do that, right? So in such a case, mean may be mean may not be the best one because mean is impacted by outliers or extreme values. So oftentimes you don't want to use mean if you have your distributions heavily skewed to the right. In such a case, we are better off using something called as a median. Median is like the central value, right? How do you compute median? You sort all the values and you pick the middle value. That's it. This is less prone to outliers, and hence we use median a lot. Again, what is the question that we're trying to answer here? Is xt greater than xc? Now, we can answer this many ways. We can compare the mean of xt and xc. We can compare the median of this. Again, there is something called as TP. We can also, TP basically means the 99th percentile value. Median is the 50th percentile value, right? We could also compute the 99th percentile value and say, I can compare the 99th percentile value. This may not be very appropriate in all situations, only in some situations. In this situation, most likely no. But the best way you can think of is, if you think about it, let's assume this is the time spent, right? Your XC is this yellow curve. This is time spent by customers who are in the control group. XT has this sort of distribution. By just looking at these two distributions, you can say, typically, again, this value is, let's say, this is the peak, right? This is the peak. By just looking at these two distributions, you can say, intuitively, you can say, hey, XT values typically are greater than your XC values. Because this distribution, this is increasing time, right? This is time increasing. If you see this distribution, not just the peak, but the whole distribution, this XT distribution is to the right of XC. right? Which means this XT, which means time spent by customers in the treatment, is typically more than time spent by customers in the control. But by just plotting this, you can't conclude. There is a catch there. So somebody might say, hey, I'll just plot these two distributions and I'll be done. There's a problem. What if your XC and XT are very few values? What if I only have 100 values here? What if I only have 100 values here? Some 50, probably only 50 values here, right? Because you're going to draw this distribution. Remember, these distributions are drawn using these empirical data or observed data. It could so happen that these 50 values are not perfect representative of actual time spent. Again, in whole of statistics, the problem is this. This is called as the sample size. The sample size could be so small that the distributions you have may not be perfect. So the reality of the challenge here is, if you have small sample sizes, how can you still be statistically confident that XT is greater than XC or vice versa? Right? That is extremely important. Now here comes a more interesting thing. Some of you are suggesting in the chat window other ideas of measuring, like confidence intervals. Right? Very interesting idea. We will come to that hopefully in the afternoon sessions. We have a dedicated discussion on that topic, on why typical A/B tests fail and what are some of the hacks that we have. We will discuss this maybe in the second part of the second session or in the third session. Okay. Again, these are all the metrics that we can use. Again, this is not the only list of metrics. You can come up with a different metric. See, at the end of the day, we want to come up with a sensible way to say, is XT greater than XC? Now, greater is something that we have to define. We can define it by comparing the medians. We can define it by comparing the means. We can define it by comparing the actual distributions. It's up to you, right? There is no one simple solution to it. So there are many valid possible, again, multiple options are both valid and possible, right? There is no one right answer. That's why there is a little bit of subjectivity in what you choose to compare. That's very important. You have to choose from a purely rigorous and a problem specific situation. Suppose I would argue that we could pick this as a reasonable. I'm not saying this is the perfect way to compare, but I'm going to argue that this is reasonable. My argument here is this, as follows. Okay, I'm going to say that this is a reasonable way to compare, not the perfect way, but reasonable. Also fairly simple, because we can compute medians fairly simply, right? Median is robust to outliers, unlike mean. And equally importantly, what this is saying here is the average, or again, median is also a measure of central tendency or average behavior, right? Not exactly mathematical average, but similar to that. What this could tell you that on an average, okay, the user who is in the treatment is going to behave better than on an average user who is there in the control. If you're looking at those average or central behaviors, we can use this mean. Again, we are only going to use this for the rest of this session because it is simple to use. They're not the same. That's the key here. Okay, cool. So now let's do one thing now. Let's continue. So what have we decided now? We understood the problem. We have observed data. Now let's go solve it. Okay. So in this process of solving it, okay, so we have empirical observations also. So what we have here is this. We have m values of xt, we have n values of xc. We can compute the median of that. We can compute the median of this. Okay, we can take the difference between these medians. So let's call the median difference as median difference observed. Okay, so let's just assume here, just for the sake of it, that this difference is 20 minutes. Let's just say it's 20 minutes. I'm just making it up just to show you the example. So now given this right, given this setup, the thing that we want to say is, how do we now, what all do we have right now? Again, I'm not directly jumping into the terminology of hypothesis testing yet, because I want you to get that intuition first. Then terminology is easy. Okay, So this is the actual empirically observed mean difference.